So today we're going to be working through some more core pure revision, this time specifically looking at volumes of revolutions. So mainly in this video today I'm going to be looking at some of the easier types. So this is mainly core pure 1 material, so this is just the AS material for the most part, so this isn't going to involve any trig, anything like the natural logarithm. So they're going to be relatively straightforward in comparison to the second year material. So let's just jump straight into this, see what we've got in these questions. So all these questions are from the Core Pure 1 textbook, so be sure to follow along if you want to work through them together. This one is from exercise 5A, question 4. So I thought I'd start with quite a nice straightforward one just so we can look at the formula and work through that. So let's do this together. So question 4. So we've got this equation here, y equals square root of x plus 2, okay? And the region R is bounded by the x-axis, the line x equals 2 and c, and it's rotated 360 degrees about the x-axis. So we've just got to find the volume of this solid. So the first thing we can consider here is what my limits are going to be for my integral. Now, before we set up the integral, my limit is going to be this other point here. So if I just put my marker on here, it'll be this point here. Okay, so this is 2, so that'll be the upper limit. This will be my lower limit. So we need to calculate that point there. And to calculate that, simply, all we're going to have to do is set y equal to 0. Or set it as y equals, y is 0, sorry. So this would be square root of x plus 2 is equal to 0. Well, if I square both sides here, I get x plus 2 is equal to 0. And then finally, take my minus 2 here, or take it as minus 2 across. So by balancing the equation, so I get x equals minus 2. So that lower point there is minus 2. So now we've got that lower limit there of my integral. We've got to use the formula, set up my integral, and then just calculate the integration. So the formula, remember, when you're doing it about the x-axis, it'll be in terms of y squared. So it's going to be v equals the integral. So my upper limit is 2, my lower limit is minus 2 of y squared. And then obviously you've got to integrate this with respect to the other variable, so it'd be dx in this case, because once we put y in here, everything's going to be in terms of x. So let's plug in y squared. So v is equal to the integral again, 2 and minus 2. Now y squared, so that's going to be square root of x plus 2 all squared, which would just simply give you x plus 2. Okay, so quite a nice straightforward one here. So if you put square root of x plus 2 in, that'll just give you, and then you square it all, you'll just get x plus 2 dx. So now, performing the integration, this is going to be equal to, oh, I actually forgot something for my integral, so I can't remember the formula myself. It should be pi lots of this. So I should have a pi here, and I should also have one here. Okay, so it's pi times the integral, and then of y squared. So it's going to be pi lots of, add 1 to the power divided by the new power, so x squared over 2. And if you've just got a constant, you just need to add the variable to it, so it'll be plus 2x. This is with respect to the limits of 2 and minus 2. Okay, so all I need to actually do now is just sub my limits in. That's going to be pi lots of, well, if I put 2 into here, so 2 squared divided by 2, that'll be 2, plus 2 lots of 2, so that'll be 4, so it's 2 plus 4, so that'll give me 6. So I get 6. I'm not quite sure why I put that in a bracket. Then we subtract the lower limit off, so if you put minus 2 in here, that'd be minus 2 squared, so 4 over 2, so that'll be 2, so minus 2 lots, and then plus 2 lots of minus 2, so that'll be minus 4, so 2 minus 4. Well, this is now equal to pi lots of 6 minus 2 minus 4, so that's minus 2, so minus minus 2. So that gives us pi times 8, or in other words, my volume, V, is going to be equal to 8 pi. Okay, and it's as simple as that when you're rotating it about the x-axis. Okay, and we haven't got any units, so my exact volume is just simply 8 pi. Okay, so that's the first one done. Quite a straightforward one. Just remember you need your pi on the outside. I actually nearly forgot that myself, so not off to a great start, but let's carry on. So the next one, exercise 5D, question 2, again from the Core Pure 1 textbook. Now the difference here with this one is that we're doing it around the y-axis this time. So we've got this curve here, y squared is equal to 4 lots of 16 minus x. Now, when you're doing it about the y-axis, the key thing is that you rearrange this to be in terms of x. So rearrange for x equals. Okay, that's the key thing about the y-axis. So let's just rearrange this first. So I can divide both sides by 4, so I get y squared over 4 equal to 16 minus x. Add x to both sides, and then subtract the y squared over 4 onto that side. So I'm going to get x equals 16 minus y squared over 4. Okay, so I've got it in terms of x now. Now, when it's around the y-axis, the formula is nearly identical. Just remember, you've got to change it slightly. So it's going to be v equals pi, so we won't forget it this time, times the integral. In this case, because we're doing the volume of this rugby ball here, my upper limit's going to be 8, using the diagram, and my lower limit will be minus 8, okay, because we want the volume of this. So it's going to be upper limit of 8, lower limit of minus 8, and then it's going to be x squared this time. So like we did with the last one, when it's about the x-axis, it's y squared, when it's about the y-axis, it's x squared. And again, it's the opposite variable with respect to, so dy. Well, x squared would just be squaring this here, so x squared is going to be 16 minus y squared over 4 times 16 minus y squared over 4. So this should be hopefully pretty straightforward. If you expand this, you'll get 256. So 256. So you do 16 times minus y squared over 4. So that gives you minus 4y squared. Minus 4y squared. You do it again here, so I give you another minus 4y squared. And then finally you get a positive y to the 4 over 16. So this can be simplified as y to the 4 over 16 minus 8y squared plus 256. Okay, so that's my x squared. So now all I can do is replace my x squared here. So v is equal to pi times this integral here with a minus 8 of x squared, where x squared is y to the 4 over 16 minus 8y squared plus 256. That's with respect to y. So now let's just integrate this. So this is going to be equal now to pi lots. Add 1 to the power, divide by the new power. So y will give me y to the 5. And then if you times it by, you're going to add to this denominator, you're going to times it by 5 because we're dividing by 5. So that'd be 16 times 5, so that'd be 80. My 8y squared here, add 1 to the power, divide by the new power. So this will be minus 8y cubed, divided by 3. And then obviously I've just got a constant, it'll be that with respect to the variable, so it'll be 256y. It's between 8 and minus 8. So now, all I'm going to have to do is plug my limits in here now. What I'm going to do is I've already done the calculations already, so what I'm going to do here now is I'm just going to put what you'd get. So, if you put 8 into here, what that'll give you is it'll give you pi lots of, so this is when I put 8 in, I'll get 16,384 over 15. Now if you put minus 8 in, now remember we subtract the lower limit off, so that'll be minus, and what you get is minus 16,384 over 15. Okay, so that's the result now of plugging my limits in. Now if you simplify this, basically you're just going to do 16,384 over 15 plus 16,384 over 15. What it'll give you is 32,768 over 15 pi. And we do have units for this one, I believe. Yeah, we're in centimetres, so that'll be centimetres cubed because it's volume. So 32,768 divided by 15 pi centimetres cubed. And that's our final result there for that one. Okay, so that's when you're doing it around the y-axis. So difference is that when you're doing it around the y-axis, this has to be x squared. So for around y-axis. Okay, so that's the key difference there. So that's that one done. Let's move on to the next one. So this one here, we've got a curve which is y equals square root of x squared plus 3. Now this one here is where you're given one limit, so I've got the lower limit of 2, but my upper limit is k. Now we're given the volume, we're just asked to find the upper limit. So, are we rotating about the y or the x? So we're doing this about the y-axis. So, remember, like we just did with the last one, if it's about the y-axis, we need to rearrange for x. So rearrange for x, that's the key bit of information here. Well, this is y equals square root of x squared plus 3. So now I can square both sides here, so that'll be y squared is equal to x squared plus 3. So then that will be x squared is equal to y squared minus 3. So therefore finally x is equal to the square root of y squared minus 3. Okay? So we've got it in terms of x now. Now we can work with the formula. So remember the formula again. V is equal to pi times the integral. So remember, we want to know what the upper limit is, which is k. My lower limit is 2. And this is for x squared. So this will be x squared dy. So we carry on. Just plugging in our x squared. Pi times the integral k to 2. Now x squared is just this. This is our x squared here, so that'll be y squared minus 3 dy. Now at this point here, let's start integrating. Now I'm not plugging in my v yet, I'm just going to do it once I've done the integration, but at this point here you can replace your v with 30 pi, because that's what we know the volume is. So this is going to be equal to pi lots. Again, add 1 to the power, divide by the power, so this will be y cubed over 3 minus 3y. With my limits of k and 2. Now this time I'm going to put my volume in. This is equal to 30 pi. So we can start solving this now. If I plug k into here, let's see what we'll get. So this is going to be pi lots of k cubed over 3 minus, where the y is, replace it with a k, minus 3k. Okay, so that's the first limit. We then subtract off the lower limit here. So 2 cubed over 3, so that's minus 8 over 3. And then we do minus 3 times 2, so minus 6 there. Okay, and this is equal to 30 pi still. So what we'll do is we'll take it up here just so we've got enough room. So we can start simplifying here. This 8 over 3 minus 6, this will simplify to give you minus 10 over 3, so minus 10 over 3, so we're going to add 10 over 3 here. So this will be pi times k cubed over 3 minus 3k plus 10 over 3. Okay, and this is equal to 30 pi still. Now we want to know what k is, that's all we're trying to find here, the value of k. Well, what I can do here now is I can divide both sides by pi. So if I eliminate those pi's, I'm just going to get k cubed over 3 minus 3k plus 10 over 3 is equal to 30. Okay, so dividing both sides by pi. Here now, I can multiply through by 3, so that's going to give me k cubed minus 9k plus 10 is equal to 90. And now I can take 90 across here and get this in terms of 0, and then we can solve it. So this is going to be k cubed minus 9k. 10 minus 90, so that gives me minus 80, is equal to 0. So here now, we've got this cubic polynomial. We're looking to find the value of k. So what we'd hope here is that we can factorise this, and that one of the expressions will be a k minus something or plus something. Obviously, in case of this, because it's above the x-axis, k must be it must be k minus something, because we need k to be a positive value. So what we'd expect here is something like k minus a times a quadratic, so k squared, I don't know, plus something k, so bk plus c, right? That's what we'd expect here equals 0. And what we'd expect now from this is that this part here would be complex, the solutions will be complex, giving us just this one k value. Now it does factorise, so this is just something that just comes with time and practice, an inspection. But what you like to get when you factorise this is k minus 5 times k squared plus 5k plus 16. Because obviously what I needed a product here of minus 80, so minus 5 times the 16 gives me that value. So therefore, the value of k will just be equal to 5. And there we have it. So this limit here, the k, is equal to 5. So that's that one done there. I've accidentally wrote down the wrong thing here, so that looks quite bad. So this is question 36. This is from the review exercise. So this is review exercise. Question 36. So that's quite a poor mistake on my behalf, but there we go. So review exercise question 36. So let's move on to the next one. This time we've got a volumes of revolution question, but it's in the context of like a modelling scenario. So what we've got here is we've got an egg timer. So that's where you've got obviously the sand, and it's going to fall after a certain amount of time. Now this is the curve C is modelled as x equals the cube root of y. So x equals the cube root of y, or y to the third. We're also told that it flows through the egg timer at a rate of 8 centimetres cubed per minute. So 8 centimetres cubed per minute. Now, they want the egg timer to empty in 5 minutes. So, if in 1 minute it's 8 centimetres cubed, 5 minutes, that would be 8 times 5, so that would be 40 centimetres cubed. Okay, that's what we'd expect. And it wants us to calculate to 2 decimal places the height of the sand that should be placed in the top half of the egg timer. So, in essence here, what we're going to be doing is we're going to rotate this around the y-axis, and what we're actually looking for is a point. So if I just change my pen colour, we're looking for a point, say, I don't know, it might be here, it could be here, might even be up here. But we're looking for a point, so we just mark it there, of where the sand would be, what that value is there, in the case that it's emptied in 5 minutes. So, change it back to white. Let's have a go at solving this. So we know we're doing it about the y-axis. So v is equal to pi times the integral. Now, the limits, if we call this point here h, because we don't know what that is, we're just looking for the height of it. And my lower limit has to be 0. That's when the timer finishes, when it runs out. So that's got to be 0 there. So my limits are h and 0, and it's going to be x squared. Now, x is y to the power of a third, so x squared is going to be y to the power of a third raised to the power of 2, so that'll be y to the 2 over 3. And obviously in this case it'll be dy. Integrate this now, so add 1 to the power, so that might as well be adding 3 over 3. So what this is going to give me is pi times y 5 over 3 divided by 5 over 3. We can simplify that in a second. Let's just put our limits back in, h and 0. And again, we know this has to be 40, this volume. So, we can simplify this. This will be equal to pi lots of, this will be 3y divided by 5. So 3y to 5 over 3 divided by 5 with the limits of h and 0. And we know this has to be equal to 40 again. So now, all we've got to do here is just sub my limits in and just solve. So, if I plug h in, this will be pi times 3h over 5 to the power of 5 over 3. But what I'm going to do is I'm going to write this as 3 over 5 times pi h. So just multiplying this through by pi now, and then subbing my limit of h in. Pi h to the 5 over 3. Now obviously if you plug the limit of 0 in here, this would just simplify to be 0, so we don't even need to worry about that. And this is equal to 40. So now let's solve. We've got 3/5 on this side, so I'm going to times it through by 5. So that's going to give me 3 pi h to 5 over 3 is equal to 40 times 5, so that's 200. And then I'm going to divide through by 3. So therefore, if we do that over here, in fact I'm going to divide through by 3 pi, so we'll forget in terms of h. So h to the 5 over 3 is equal to 200 divided by 3 pi. I mean, you could have divided it through by 3 and then divide it by pi, but we might as well do it all in one step. And then finally, to just get this value of h, we need to raise it to the reciprocal power. So remember, if you've got like x to the power of half, you raise it to the power of 2. So in this case, I'm going to raise everything to the power of 3 over 5. So therefore, h is going to be equal to 200 over 3 pi to the power of 3 over 5. Okay, now we actually want this to 2 decimal places, so we need to put this into our calculator. And what you'll get is if you put this in your calculator, you get 6.25. And yeah, we're in centimetres, so 6.25 centimetres. Okay, so that's the height. So this point here on the egg timer is 6.25. Obviously, it'd be a bit higher, but yeah, height of 6.25. So that's a modelling scenario question. So exercise 5D, question 4 there. I think we're on to the final question here. This is from the mixed exercise 5, question 1. So this one, again, is just a quite nice basic one. So we've got this equation, y equals x squared times the square root of 9 minus x squared. And what we're rotating it about, so we're doing it about the x-axis. So another one about the x-axis. So y is equal to x squared times the square root of 9 minus x squared. So let's use the formula now. V is equal to pi times the integral of my limits. So it's going to be 3 as my upper limit, and my lower limit here is the origin, so 3 to 0. Of y squared in this case, so y squared, and again dx. So y squared, if you squared this expression here, remember treat each one separately. So x squared squared, that'll give you x to the 4. And if you squared this expression here, so the square root of 9 minus x squared, you'll just get 9 minus x squared. And remember, we multiply these together, so it'll be 9 minus x squared times x to the 4. So if we sub that in, that's going to be v equals pi times the integral 3 to 0 of x to the 4 9 minus x squared dx. So now we can just simplify this. I'm going to multiply this expression out here. It's going to be equal to pi times the integral. So this would be 9x to the 4 minus x to the 6. So just some basic indices here. dx. And then we can actually integrate. So add 1 to the power, divide by the new power. So this would be 9x to the 5 divided by 5. Add 1 to the power, divide by the new power, so that'd be x to the 7 divided by 7. And my limits are 3 and 0. So all I've got to do now is plug 3 in here. Obviously, if I plug 0 into here, this expression is just going to come out as 0 anyway. So we're going to subtract nothing off. So all I've got to do, nice and easy, just plug my upper limit in here. So this is going to be equal to pi. Now, I've already done all this anyway. But if you plug 3 into here, what you should get is pi times 4,374 over 35. So therefore, the volume V is equal to 4,374 pi over 15. And there we have it. That's the exact value, again, it's in terms of pi, of the volume of the solid that is generated. So I hope that's been helpful. If it's helped, be sure to subscribe, like the video, leave me any feedback in the comments below. Cheers, guys.